Welcome back to ECE 442-542. This I'm entitling a root locus for the special case of two poles and one zero, where I have two real poles to the right of a real zero, and that's the configuration that we will be talking about. In this case, we know what particular line segments belong to the root locus. We'll have one line segment between P1 and P2. Those will now come together, and they will obviously have to move off the real axis when they reach each other, or the breakaway point, and that will occur at a relative maximum, and that will not be right halfway between P1 and P2. It will actually be the geometric mean, or that breakaway point will be determined by the distance, this radius from the zero. And once we have that breakaway point, which we can compute as the square root of L1 times L2. L1 is the length from the zero to the first pole. L sub 2 is the length from the zero to the second pole. The geometric mean will now be used to determine the location of the breakaway point, Z sub B, from the circle's center, which is the zero location, Z, or Z sub B. The breakaway point is now Z, the zero's location, plus, maybe I should say that's Z sub 1. Let me just say Z sub 1 plus the radius, where the radius is this geometric mean, or the square root of L1, L2, or L1 times L2, where L1 is P1 minus Z, the distance between P1 and Z1, or the distance between the first pole and the zero, and L sub 2 is the distance between the second pole and the zero. This breakaway point now establishes the radius, where the center of the circle is Z1. The radius now gives us, and I'm not sure that I'm going to be able to sketch this. You can laugh as much as you want, but this is now supposed to be a circle of radius r sub radius, and with that radius, I hope you see that the reentry point is going to be to the left of the zero, Z1, or the center of our circle, by the amount of that radius. So if we now have two poles, real poles, to the right of a zero, a real zero, we can now compute this breakaway point by simply finding those two lengths and computing their product and taking the square root. That now gives us this radius, r radius. The r radius will now be moved relative to the center of our circle of the root locus. So this isn't dashed anymore. This is actually now should be our root locus sketch, which gives us our closed loop poles as we adjust the gain K in our system. And then once they get to the reentry point, one goes to the right towards that zero, the other one marches off to the zero at infinity. And that's really what you need to know for sketching these root loci for the special case of two poles, real poles to the right of a real zero. And that's what I'm trying to indicate here with this picture. Maybe it's a little cleaner, but our radius, again, is this computation from zeros of the zero and the poles P1 and P2. The breakaway point, Z sub B, is to the right of the zero. So let me now again establish notation. Let's say that's Z1. And the reentry, which I'm calling Z sub R, is that same radial distance to the left, or on the left-hand side of that real zero, Z sub 1. And Just to repeat, that root locus shape for this special case is a circle with the center at the 0. So now if you had your compass, you would put the rotational point of your compass right at that 0 location. You would put the pencil point of the compass at the breakaway point. That now defines your radius, and you now with your compass could simply sketch that circle, and that would now establish your reentry point. And where those are relative to the unit circle would obviously then impact or determine the range of K for stability if the system is even potentially stable for that combination of poles and zeros. A special case would be if the two poles are actually at the same location. I've shown them a little bit off of each other, but that's just to emphasize that we do have two poles there. And in fact, now this is a terrible sketch, but the radius again would be easy to calculate. It would just be the difference or the distance between the real 0, let's say Z1, and these poles that are both at P1. That distance should be easy to calculate once you have the poles and zeros, and now the reentry will just be one radius away on the left-hand side of that 0, Z1. If you think that through a little bit, you can see that you have the same circular shape even if your poles are complex conjugate pole pairs, and you now have 1, 0 on the real line. You now could, if you follow that highlight, you could rotate those, or you now have the radius, and that's just going to be this difference between the 0 and this pole P1. You could now compute that radial distance, or the length of that line, since you know that that point, or I'm sorry, the length of that line segment is P sub 1 minus Z sub 1. You could find the length of that two-dimensional vector, or the magnitude of that complex number, and use that now to determine your reentry point. In this case, in this picture, you would not have a breakaway point. You're never starting on the real line with your poles, but you would have a reentry point, and that reentry point would be one radius to the left of your real 0. Let's now see if we can justify why we have this particular geometry, or this geometric shape of a circle for this type of two-pole 1, 0 collection of poles and zeros, where the two poles are actually to the right of the 0. And here I'm just saying, let's let one pole be at A, the other pole be at B, and for simplicity, that's why I'm saying an easy example, let's put our 0 right at the origin. And so our system, the transfer function, the open loop transfer function, which we have been calling G bar, would now be Z over the two factors Z minus A and Z minus B. Well, we know the magnitude condition. That just says that the magnitude of Kg bar is equal to 1. We can now solve that for K, and we now have the magnitude of the of the pole factors over the 0 factor. We can multiply out the pole factors in the numerator of this expression for K, and we now have Z squared minus the sum of A plus B. Those are our pole locations, real poles, plus their product, AB. Now, if we want to find the breakaway point, that occurs at a relative maximum. So now what we would do, we could numerically evaluate this for values of Z between A and B and find where is K a relative maximum between A and B. That would be our breakaway point. We could do it analytically with some calculus by finding the derivative of K with respect to Z. This now will just use the quotient rule. So now if we take the derivative of the numerator, which is now 2Z minus the quantity A plus B, times the denominator, which is z, minus the numerator, which is z squared minus a plus bz plus ab, times the derivative of the denominator, which the derivative of z with respect to z is 1, all divided by the denominator squared. To find the relative maximum, we would set that dk dz to 0, or from the numerator, we now just need to set that equal to 0 and see what we end up with. So we now have 2z minus the quantity a plus b, all of that times z. That's our first piece, which under the curly bracket, I've multiplied or distributed that z through. I have 2z squared minus the quantity a plus b times z. I've now distributed that negative sign in the second bracketed term, and I have plus z squared plus the quantity a plus b times z minus ab, and all of that again is equal to 0. You can see that we can combine the z squareds. So we now have 2, and I have to correct my algebra, don't I? So this is now a minus z squared. So I have 2 minus 1 times z squared. The linear term in z, I have a minus a plus bz, and I have a plus a plus b, that quantity times z. Those cancel, and I am left with minus ab, my constant piece, which is equal to 0. Well, 2 minus 1 is just 1, so that now gives me z squared minus ab equaling 0, or z squared is equal to ab, and I'm now trying to find the value of z that satisfies that equation. Well, I could take the square root, and in fact, I could take plus or minus the square root. The plus piece would actually be the relative maximum. The minus piece would be the relative minimum, and so in this particular picture, our breakaway point would be here, and our reentry point is this minus square root of AB, and this is now the square root of AB for the breakaway, because we know that our root locus is going to have a segment between the two poles. We'll have another segment to the left of the 0. We will break away, have our circle with the 0 at the center of that circle. Then they will re-enter. One will go to the finite 0 at the origin. The other one will zip off to the infinite 0. And now we'll just have to worry about where are those branches of our root locus relative to the unit circle. But all of that now should be explaining why, in general, we just have to worry about finding the geometric mean between or relative to these two lengths, L1 and L sub 2, where L1 is the length between the first pole and the 0. L sub 2 is the distance between the second pole and the 0. And with that, we can now compute our radius, quickly finding the breakaway point, the reentry point, and then we will have to determine what our values are on K relative to this root locus pattern or shape and the unit circle.